So let's take a look how to process imported transient waveforms. In this case, I open a flyback transformer template, and I will demonstrate how to work with waveforms on this case. So first, let's take a look on the file format that we need to import. So I clicked on the template, this folder name. The case folder has opened. I go to cached, scroll down, and there's a file which is called waveform dump. This file is the original waveform that was imported for this case. Further, there's a source file that has processed waveforms that are used by TRAFOLO, but we will look on that a bit later. So now I open waveform dump, and this file was created by Circuit Simulator, and the way how Circuit Simulator stores this data is column-wise. So the first one corresponds to the time of primary current, value for primary current, time for primary voltage, primary voltage for the primary, etc., etc. So you can import in those time series in any order, so order doesn't matter, but keep in mind that the first row is reserved for the name of this time series. So those names will be later used for by you to identify which corresponds to which. Also note that the time should not start from 0, it can start from any point. In this particular waveform, I deleted all unnecessary like inrush periods and usually I keep just a few last periods where I know that the transient waveforms have reached some steady state. Next, so once we import the file, so we click import, I put the path name here. So once we import the file, TRAFOLO will put time primary source, secondary source, just in the same order as they appear in the file, which is not the case, the way how we should select it in this case. So make sure that the time corresponds to the time. The primary source in our case is current, so this is correct. And for the secondary source, we also need current, so I will choose secondary current. Now, on this preview window, you can see two waveforms, two groups of waveforms. So one is original, which is like the original waveform file that you imported. Let's take a look on it. The issue with this original waveform is that, for example, when we have the sudden change in the amplitude, there are no points. So very often circuit simulators, they do not resolve such a very steep changes in amplitudes, which is not the case in FEM simulation, because in order to account, for example, for the chord loss, we would need to resolve this sudden change. And therefore, there's another set of waveforms that we call interpolated. So those are already post-processed waveforms, and as you can see, that in TRAFOLO we add additional points on those very steep slopes, so that we get just additional resolution for those steep changes. The way how it is achieved is by the setting which is called optimize time steps. And there are different algorithms that you can use to optimize those time steps. The first one just puts time steps in identical time steps, so they're equal sizes here, which is not optimal for this case, especially if you, for example, enable the original one. You see that if we apply identical time steps, then we do not get optimal time steps for FEM simulator. There's another algorithm. As you can play with them, you basically will usually likely choose the fourth one. It's the most robust. What it tries to do, it tries to identify the vertices of, or basically the points with the highest derivatives, where this waveform has the steepest change, and then adds points there. And then tries to find those regions where there is the steepest change in the amplitude and adds additional points, as in this case. So if we, for example, zoom in, we can see that here in this region where we have the steepest change in the amplitude, TRAFOLO has added additional points. Also, what might be very useful for you, so notice that there's like a special button to scale it to a visible area. Also, what could be very useful for you is to skip first period from averaged losses. When you will calculate transient simulation with multiple periods, oftentimes the first period is a bit spoiled because you cannot always match the initial phase to correspond to the magnetic flux in the core to zero. So losses and current amplitudes or magnetic flux amplitudes in the first period might slightly differ from the following ones. So we can skip the first period from the averaged losses. So averaged losses will be calculated from the second period and on. For example, if in this case I have two periods, then the losses would be calculated only for the second one. But if I increase the number of periods, like for example from 2 to 4, then the average losses would be calculated for the 3 remaining periods. So as you can see here, there are additional parameters that you need to set. So here we will need to tell what is the fundamental frequency, what is the switching frequency. With this one, the software knows where to cut those periods. If, for example, I would wrongly choose this period, for example, let's instead of 150 K, I would set 50 K. Then you see that instead of two periods, we see 3 times more. So it should be like six periods here. Let's return back. So in order for the software to identify the length for each period, we need to provide this frequency here. So number of periods that needs to be simulated in the transient simulation is defined here. Points per period is just a rough number. So it will not be identical to, for example, 37, but the software will try to approximately match the number of points that you specify here. However, the total points for the simulation is 55. And last, there is a by points option, with which you can basically apply a shift point-wise to your waveform. And the reason why you might need such shift is because ideally, in order to reduce the inrush current or inrush voltage at the beginning of your simulation, you want to match your phase of your waveform to the phase where the magnetic flux in the core is zero. Because when we run the simulation, it always starts with magnetic flux zero. If you don't do so, then you may have some DC bias for magnetic flux. And finally, you will find that there's a discrete Fourier transform options. Number of harmonics just tells how many harmonics you want to use to calculate winding losses. You can see those harmonics here under the DFT. And basically the way how it works, so from those amplitudes, from those DFT amplitudes, the software calculates effective resistance and sorry, not resistance, but effective RAC RDC, and then applies this effective RAC RDC on the entire waveform and calculates winding losses for the transient simulation. So it means it's only for leads and stranded wires. Obviously, for solid wires, the losses would follow from the actual current distribution in the windings. Also, if you want to convert transient simulation into harmonic simulation, you can specify how many harmonics you want to apply in the harmonic simulation and click Harmonize. I click Harmonize. It just asks me whether I want to switch the simulation type to harmonic. I click OK. And now you can see that the software has basically applied this DFT and set up harmonic simulation for me. So this is fundamental frequency, and those are all the harmonics, also including a slight DC bias that was inside that transient waveform. However, note that flyback transformer case is not good for harmonic simulations, because it by definition has this DC bias, and it is not optimal for harmonic simulations. So going back to the source file, if you open the source file, this will be time dt primary secondary values used in TRAFOLO.